Hello and welcome. So recently we've been talking about the simple linear regression approach to understanding the linear relationship between two variables that we're interested in. So one dependent variable or outcome variable and one independent variable or explanatory variable. In this lecture, we're going to begin to expand our framework by talking about how we can take into account multiple independent variables that we're interested in, so multiple variables that could affect the outcome that we care about. This framework is going to be called multiple linear regression. Again, we're going to be considering the linear relationships between variables, but this approach is going to allow us to take into account lots of different independent variables. This is a popular approach because it allows us to control for confounding variables, which itself allows us to isolate relationships between variables that we're particularly interested in. So just to recap, the simple linear regression approach is a bivariate approach. It allows us to take into account two variables, one independent variable and one dependent variable. Multiple linear regression is a multivariate approach. It's going to allow us to take into account still just one dependent variable, y, but multiple independent variables, so x1, x2, and so on. The example that we're going to be using throughout this lecture is a bit of a trivial one. It's kind of a silly example, but hopefully it's going to allow us to illuminate the key concepts in multiple linear regression. So let's say that we are interested in predicting how much books weigh. And so we have data on the weight in grams of 15 different books. We also have data on the volume of those books in centimeters squared, so the length of the book times the width of the book times the book's height. And then we also have information on this categorical variable, whether the book is a hardcover or a paperback. So this final column in the data set here indicates whether a book is hardcover with the letters HC and paperback with the letters PB. So let's say that we wanted to do a simple linear regression and use the volume of a book to predict its weight. So it should make sense intuitively that how big a book is in terms of volume, how wide it is, how long it is, how thick it is, should be pretty tightly correlated with how much the book weighs. So this scatter plot here shows this relationship between weight in grams and volume in centimeters cubed. And so the regression equation that we get from this simple linear regression is that the estimate of a book's weight is equal to 108 plus 0.7 times the volume of the book. And we get an R squared value of 0.8 or 80% from that simple linear regression. So take a look at these options below and see which one of those options is a correct statement about the regression that we just estimated here. So the correct answer is that books that are 10 cubic centimeters above the average higher in volume are expected to weigh 7 grams more than average. So we can see in the regression equation that the coefficient for volume is 0.7. And we know that what that means is that a 1 unit increase in volume corresponds to a 0.7 unit increase in weight, the dependent variable that we're interested in. Now, because our relationship that we're estimating here is linear, this relationship is something that we can scale. So if the relationship between volume and weight is that a 1 unit increase in volume corresponds to a 0.7 unit increase in weight, we can multiply both of those by 10 and the relationship still holds. So a 10 unit increase in volume corresponds to a 7 unit increase in weight. Let's talk briefly about why these other options are incorrect. So option A says that the weights of 80% of the books can be predicted accurately using the model. This is not the correct interpretation of R squared. R squared tells us that 80% of the variation in the dependent variable y can be explained by the model. This does not mean that the model exactly predicts 80% of the values of the dependent variable. So that's an important distinction to make. The regression line doesn't capture 80% of the data points, right? 80% of these data points don't lie exactly on the regression line. But the regression line does give us this sort of useful approximation of the relationship between these two variables in a way that explains 80% of the variation in the dependent variable. So that is why option A is not correct. Option C says that the correlation between weight and volume is equal to 0.8. So the correlation is not the same thing as the R-squared value for this linear regression, so that's why this option is not correct. And option D says that the model underestimates the weight of the book with the highest volume. So the difference between the estimate and the observed value is just the difference between that observed point and the regression line. So we can see that the book with the highest volume has a volume of a bit more than 1,400 centimeters cubed, and the regression line goes above that point. So if you were to follow up from that data point farthest out to the right in this scatter plot, you can see that the predicted weight for a book with that volume is quite a bit higher than the observed weight for the book of that volume. So the model actually overestimates the weight of a book with that volume of about 1,400 cubic centimeters. So if we take that data that we had represented in our scatter plot and we estimate a regression where the weights of books is our dependent variable and volume is our independent variable, this is the sort of output that we would get in R. So R gives us our estimates of the parameters, our beta naught intercept parameter and our beta 1 parameter for volume, as well as standard errors for each of those and t-values, and then the p-values that are associated with those t-statistics. You should notice that the p-value for volume is in scientific notation, so 6.26 times 10 to the negative power of 6, which is equal to 0.000000626, so a very small p-value on volume. So what that means when there's a very low p-value, that means that volume is a statistically significant predictor of the weights of books. So remember that when we're talking about linear regression, the null hypothesis is that the beta parameter, the slope parameter for the independent variable is 0. That's the null hypothesis. When we have a really low p-value, that means that we reject the null hypothesis in favor of the alternative hypothesis that there is a slope with sort of a meaningful, that represents a meaningful relationship between those two variables. So because this p-value for volume is so small, we can see that there is a statistically significant relationship between volume and book weights. So this scatter plot represents the same data that we have been talking about, with the one difference that now we've differentiated between data points that represent hardcover books and data points which represent paperback books. So the hardcover books are represented by these blue squares and the paperback books are represented by these green triangles. So take a look at this scatter plot and see if you can identify whether there is a different relationship between weight and volume depending on the kind of book that we're looking at, whether it's a hardcover or a paperback. So it should be pretty clear from this scatter plot that paperbacks generally weigh less than hardcover books after we take volume into account. So if a paperback book and a hardcover book with the same volume are compared to one another, the paperback book is likely to weigh less than the hardcover book even though they are the same size. What this tells us is that taking into account the type of book that we're dealing with, whether the book is a hardcover or a paperback, is important. This is a meaningful variable when it comes to the relationship between weight and volume, because paperbacks in general weigh less than hardcover books do. So if we want to put this additional variable into our regression model, we can, and this is what that output would look like. So we get estimates for the parameters that we're interested in, the intercept of our regression line, as well as slope parameters for both of the independent variables that we've included in this model. We also get standard errors around each of those estimates, as well as t-statistics and p-values. And next to each of the p-values in this far right column, we also have these stars that are a quick reference for statistical significance. So if the p-value for the parameter is less than 0.1, there will be a little period out next to this p-value. If it's less than 0.05, there will be 1 star. If it's less than 0.01, there will be 2 stars. And if it's less than 0.001, there will be 3 stars. So we can see from this output that both of our independent variables, volume and the type of cover the book has, both of those are highly statistically significant with p-values less than 0.001. Now, recall that when we were talking about how we use categorical variables in a regression model, we noted that when we use a categorical variable, we have to leave one level out as a reference. So if I have 2 levels of my categorical variable, I can add one dummy variable to my model that is equal to 1, indicating any time we see that particular value of the categorical variable, and then we leave the other category as represented as zeros in that dummy variable. So based on this output here, based on how we've specified this model, which level of the cover variable is the reference level? And the answer is that hardcover books are the reference level. So we have an indicator for whether the cover is a paperback, which means that this is a variable that is equal to either 0 or 1, and if the book is a paperback, the variable is equal to 1. If the book's a hardcover, the variable is equal to 0. So hardcover is this omitted reference level. So just to check your understanding, make sure that you understand what role each of these variables is playing in the regression model. I've given you a couple of options here, so pause the video and select the right one. So the variable that we're interested in explaining is how much a book weighs, and we're using 2 independent variables to predict this. One of them is the volume of the book, and the other is the book's cover type. So if you don't understand that, it would be a good idea to sort of go back to basics and make sure that you understand the difference between independent and dependent variables and how we use independent variables to predict values of dependent variables. So, assuming that you understand that, let's go ahead and move on and talk a little bit more in depth about this particular model. So remember that our regression output gives us information for the equation of the regression line and gives us a way of predicting particular values of the dependent variable. So the estimated value of weight is equal to the intercept, 197.96, plus 0.72 times the volume of the book, minus 184.05 times the type of cover that the book has. So let's talk about, for different values of cover, what this equation looks like. So remember, our categorical variable for cover is equal to 1 when a book is a paperback and equal to 0 when a book is a hardcover. So the second term, which is negative 184.05 times cover, that term is going to go to 0 when we're dealing with a hardcover book. So for a particular book that we're interested in, our predicted value of weight is equal to the intercept plus a 0.72 times the volume of the book minus 0, right? Minus this slope term for the cover variable times 0, because the value of cover is 0 when our book is a hardcover. So that term just goes away when we're dealing with a hardcover book. When we have a paperback, that cover variable is equal to 1. So our estimated value of weight is equal to the intercept plus 0.72 times the book's volume minus 184.05. So this is indicating for us that paperback books on average are going to be weighing less than hardcover books. So this is sort of the average difference between the hardcover book weights and the paperback book weights. So when we're dealing with a paperback book, our estimate of the weight of the book is going to always be lower when we're holding volume constant, because we have this negative 184.05 term that becomes part of our estimate of the book's weight. Another way to think about this is that including this categorical variable that lets us distinguish between hardcover and paperback books lets us have a way of having a different set of estimated weights for hardcover books and paperback books, which you can see in this plot here. So we can see that because we always expect that hardcover books are going to weigh more on average than paperback books, the linear estimations of weights through these data points are going to be different depending on whether we're considering hardcover books or paperback books. And essentially this is what we're doing when we control for cover type in our regression model. We're giving ourselves a way of adjusting our estimated weights depending on the type of book that we're dealing with. So let's talk about how we interpret the parameters that we find in a multiple linear regression model. So these are going to be a little bit different than in a simple linear regression, just because we have more independent variables to take into account while we're doing our interpretation. So let's take a look at each of these in turn, starting with the slope parameters of our independent variables. So looking at volume first, we can see that our coefficient on volume is 0.72. Now, in a simple linear regression model, what this means is that a 1 unit increase in the independent variable volume is associated with a 0.72 unit increase in the dependent variable. When we have a multiple linear regression model, we need to add just one more condition, one more caveat to that, which is all else held constant. So all of the other variables in the model, in this case we only have one other independent variable in the model, but with the other independent variables held constant, a 1 unit increase in volume is associated with a 0.72 gram increase in weight of the book. So what that means is that if we're examining the same type of book, right, if we're examining just paperbacks, a 1 unit increase in volume is associated with a 0.72 unit increase in weight. If we're examining just hardcover books, same thing. When we're looking at the slope of cover, all else held constant, the model predicts that paperback books weigh 184 grams less than hardcover books. So the coefficient for cover is negative 184.05. And remember that a 1 unit change in cover is just toggling back and forth between paperback and hardcover. So when we move from a hardcover book, which is the cover value 0, to a paperback book with cover value 1, the expected change in weight is negative 184 grams. So that's what a 1 unit change in that independent variable means. So when we go from 0 to 1, when we go from hardcover to paperback, we expect a change in weight of negative 184.05 grams. So categorical variables are pretty easy to interpret in this way. When we have a dummy variable that just takes on the values 0 and 1, just sort of tells us on average the expected difference in the outcome for those different levels of the categorical variable. And then finally we have the intercept. Our intercept is equal to 197.96. The intercept is equal to the predicted value of the outcome when all of the independent variables in the model are set equal to 0. So when cover is set equal to 0, that means we have a hardcover book, and when volume is set equal to 0, that means we have a book with no volume. So this prediction, this meaning of the intercept, is that hardcover books, right, cover equal to 0, with no volume are expected on average to weigh 198 grams. Now remember that sometimes the intercept is not something that makes sense substantively. It is a point for our regression line to cross over the y-axis. But a lot of times the intercept just isn't meaningful when the value of the independent variables that are associated with the intercept just don't make sense. So obviously it doesn't make sense to think about there being a book with no volume, and not a physical book anyway. And so the intercept is not something that makes sense in a real world situation, but This is where that regression line is going to cross the y-axis at 197.96 grams. So let's say that you have a book with a volume of 600 cubic centimeters and the book is a paperback. You have all the information that you need in this regression table to calculate an estimated weight of that book. So go ahead and look at these options and see which of these is the correct equation for calculating that estimated weight. So our estimated weight is the intercept plus the slope parameter for volume times the book's volume, 600 cubic centimeters, minus the slope parameter for cover times the value of cover. Since we have a paperback book, the value for cover is 1. And so when we solve all of this out, we're going to end up with a predicted weight of 445.91 grams for a book that is a paperback with this particular volume. And that is bringing us to the end of our lecture on multiple linear regression. Thank you for tuning in, and I will see you next time.